So we've been looking at Taylor series and how to take a function and create a Taylor series for that function. And we've looked at some graphs of the Taylor polynomials, and it appears that as you go up to higher and higher order in those polynomials, they tend to look more and more like the function. Now the question we have yet to answer is, as you go to infinity and you get the entire series, is the series the same as the function? And what we need to do that is Taylor's theorem. So I want to look at this, and we'll use it actually in two different ways. So let's take a look at the theorem. There's some preconditions on this theorem. F and its first n derivatives have to be continuous on that closed interval from a to b. Most of the functions we deal with are continuous everywhere, so this is not a big issue. And then that last derivative has to be differentiable on the open interval from a to b. If those conditions sound kind of familiar, it's because that goes back to the mean value theorem. Actually, Taylor's theorem is a generalization of that. If you look at the proof of Taylor's theorem in the book, it's basically mean value theorem over and over. So let's take a look. What does Taylor's theorem tell us about the function? So there's a lot of notation in here. So first, I just want to make sure we understand all the pieces in this formula. So starts off f of b. So that's going to be some value you're interested in. So maybe you want to know the square root of e or something like that. So the function's e to the x, and you're wanting it at 1/2, right? E to the 1/2. So there's some value you'd like to have. And then what is this saying? If we look at this first part, that looks exactly like the definition of a Taylor polynomial. Notice it goes from 0 up to n, not to infinity. So this is finite. So to simplify things here a little bit, let's point out that this piece is simply the nth order Taylor polynomial evaluated at b, right? So if we wanted to know some approximation of a function at a point, we would use the polynomial, right? That's the idea of Taylor polynomials. And then this second bit over here, this is the key part that's being added on here. It's saying that the actual value, the value that we'd really like to know, the exact value of the function, is the polynomial plus a little bit. So you can think of this as the error term. We're going to use a big R for remainder like we've done in the past. So it's telling us that if you want to know the value of a function at some point, it is equal to its Taylor polynomial at that point plus some error. And the key part, really, the thing that we're going to be focusing on is this. What can we do with this formula so that we can say something about the error? And we're going to do two things. One is, if we can get an upper bound on this error, then we can say something about how good our approximation is. So if we're going to approximate sine at 0.1, that's great, but how good is the approximation? Well, this term is going to allow us to put an upper bound and say, well, we're not off by more than such and such. So we'll use this for error bounding. We've done some error bounding in the past. Now we'll be able to do error bounding with Taylor approximations. The second thing is what I started off with is, if we can prove that as n goes to infinity, so as you go to higher and higher order Taylor polynomials, if we can prove that this term goes to 0 as this goes to infinity, well, as n goes to infinity, the Taylor polynomial becomes the series. And if this is 0, that means the function at that point equals the series at that point. So the idea is we'll be able to prove under what conditions the series actually equals the function. So we get really two features from this theorem. So let's look at all the quantities in this formula just so we understand what they are. And we'll just list them out so we're clear. So first of all, there's reference to a function, right? F of x. So that's the thing that you'd like to approximate. Sine, cosine, e to the x, natural log, hyperbolic cosine, whatever it is. So this is the function to be approximated. And then there's an n in there. Well, actually, yeah, let's just go to n. So what is this? This is the nth order Taylor polynomial, right? That's what the n tells us here. We're going up to the nth order term there. So that's the order of the polynomial to be used. So you might be using a fourth order, fifth order, sixth order, whatever. Taylor polynomial is your approximation. And then so we have a B and an A and a C. A is the A that we've been talking about. Remember, when we create these Taylor series, we center them somewhere, right? So for e to the x, it was at 0, cosine was at 0, sine was at 0, natural log was at 1. So that's the good old center from before. So this is the center of the polynomial. B, well, notice we're talking about f at some actual point. So if we were going to approximate sine somewhere, say sine of 0.5, then we're wanting to plug 0.5 into sine, but instead we're going to plug it into its polynomial. So that location where we'd like to approximate it is what the B is. So this is where we want to approximate f. Now the very last thing in here is C. If you look here, this error term looks a lot like it would just be the next term in that polynomial, right? It's got the next derivative over that factorial, b minus a to the n. But that derivative is being evaluated not at a, like we would in the normal, but at c. And we don't know what c is. If we look at the details, the statement says that there's a number c there between a and b. That's all we know. So c is unknown. All we know about c is it's somewhere between a and b. Oops, a and b. And we'll never know what c is. If we knew what c was, we could just calculate the error and there'd be no error, right? We could just add it on to the polynomial and we'd have it exact. So that's when I mentioned earlier about if we could put an upper bound on this. So we won't know what c is, but if we could bound that derivative, we know c is somewhere between a and b. So if we can put an upper bound on that derivative, we can put an upper bound on that error. And that's how we're going to use this. So even though we don't know what c is, the fact that we know that it's somewhere between a and b allows us to narrow our interval down and put a bound on our error. So let's just set one up just so we kind of see what all these quantities are in practice. So say we were going to approximate square root of e. I think I mentioned that already a couple of times. So that is really the exponential function e to the x evaluated at 1/2, right? And let's just pick a Taylor polynomial, just sort of arbitrarily. Say we were going to approximate it using the third order, whatever I can fit on the board here. 1 plus x, right? The series for e to the x goes 1 plus x, which is 1/2 in this case, plus x squared over 2 factorial plus x cubed over 3 factorial. So let's just say we stop there. We could compute that. It's just multiplication and division and addition, right? So we've taken a transcendental and approximated it. So this, thinking of our formula, this is the polynomial, right, that we're talking about. And then Taylor's theorem tells us something about how to bound this error. But right now, I just want to make sure we understand what the quantities are here. We'll actually use this in another video. So first of all, when we're trying to identify these things, and I recommend doing this first, what is the function? The function that we're using here is e to the x. We'd like to approximate that function. Where would we like to approximate it? At a half. Where do we center this thing? Well, remember, e to the x, we centered at 0, so a is 0. What's the degree, or order, I should say, of this polynomial? Well, we're going up to the third degree term there. So this is a third order Taylor polynomial. So those are the key quantities we would need. The thing is, lastly, c, we don't know what c is, but it's somewhere between 0 and a half, somewhere between a and b. So if we computed this, it would be an approximation of square root of e. Now, how good is it? Well, that's what Taylor's theorem says. In this case, r sub 3 at a half is the n plus 1 derivative. So the fourth derivative of f. So the fourth derivative of e to the x. Well, that's easy. All derivatives of e to the x are e to the x. So the fourth derivative evaluated at c there. So the fourth derivative at c over 4 factorial and times b minus a to the fourth power. Now, typically, what we would do is then try and find an upper bound on this quantity right here. And we know everything, right? We know everything. We'll always know everything except for this part, right? We know n, we know a, we know b. It's the fn plus 1 at c that we don't know because we don't know c. So typically what we'd be looking to do is put an upper bound on the magnitude of this. So this error could be positive or negative. So we'll look at the absolute value, which in this case we have 4 factorial. Let's just write this out. We've got e to the c. I'll kind of separate out because that's the part we need to bound, right? So it's the absolute value of e to the c. That's the part we still don't know. And then we have 1 over whatever 4 factorial, which is 24, times 2 to the 4th, 2, 4, 8, 16. OK. Now, what do we need to do? We need to say something about how big e to the c could possibly be. Well, let's think about this. Let's draw a little picture here. We know c is somewhere between 0 and a half. So I don't know what c is, but it's somewhere in between there, right? I know what e to the x looks like. From 0 to a half, it's increasing, right? So c is somewhere in here. So e to the c is somewhere at the height of this curve somewhere. Well, wherever it is, it's less than that, right? The highest point there would be at e to the half. So here's where our bounding comes in. So I can say that my error magnitude, because we took an absolute value, so our error magnitude is less than, well, I know whatever c is, e to the c is less than e to the half. And then we have 1 over whatever 24 times 16 is. Now, there's a slight problem with e to the x. Seems like we're done here, right? OK, great. This would be our approximation. We know we're not off by more than this. But what were we trying to do in the first place? We were trying to find an approximation of square root of e, this thing we don't know. right? We don't know the square root of e, but we know whatever we got, it's not off by more than the thing we don't know times 1 over 24 times 16. So this is a little bit of a problem. I do not want you to leave your answer like that because that's a bit of a circular argument, right? You're using the thing you don't know as a bound on the error on the thing you don't know. So we can prove via integration somewhat easily that e is between 2 and 3. So for the rest of this course, because really we haven't proved what the value of e is in this course. So from now on, you can use the assumption that e is somewhere between 2 and 3. Don't assume you know any more than that. Obviously, we learned a bunch of digits of this in algebra, 2.71828. But for our purposes, I want you to put one more bound on here and say, well, e is less than 3. So this is less than 3, less than 3 to the half, or square root of 3. And then 1 over 24 times 16. What's that? 24 times 10 is 240. 24 times 6 is 144. So 240 plus 144 is 384. And so there's our upper bound on our error there. And we're not answering it in terms of e. So this would be the approximation. And we're using Taylor's theorem to say, whatever this comes out to be, when we compute it, we know that we're not off from the real answer by more than that in absolute value. We might be over, we might be under, but we're not off in magnitude by more than that. All right. When I started off, I said I wasn't going to work through this whole example, but I did. So now you have sort of a description of what Taylor's theorem says. And here we are using it to do an error-bound problem. We will next look at using this to prove that the function and the series are identical. We'll prove that this is converging to the function as n goes to infinity.